You might be wondering what that was. And what that was a very shoddily put together toy car, or more accurately, a model of a car that is not complete. And why do I have this shoddily put together model of a car? Well, it's because I want to just frame the idea of G-force and what this all means in relation to cars and other situations before I get into it. So just to start, what G's really are, it's just a measure of acceleration. 1 G is equal to the Earth's force of acceleration, which is 9.81 meters per second squared. So when I drop this car, again, it's experiencing, give or take, 9.81 meters per second squared of acceleration. This may change due to air resistance or some other outside factor. Maybe I pushed the car down when I dropped it instead of just dropping it. So it's not perfectly 9.81, but that's around what it is experienced in terms of acceleration in the downwards direction. Now, day to day, the average person will experience like 1.6 G's of acceleration just constantly. So that's just the normal amount of G's someone will have. And we're going to talk about a few examples, including a car taking a turn in NASCAR, a spaceship taking off, and most importantly, a fighter pilot, which is the most commonly known example of G-force, because I think when most people thinking about G's, they're thinking about, oh, that's what pilots go through, that's why they have all the special equipment. And then I'm going to talk about why they have that special equipment, why they and other professions that deal with high levels of G's take training courses, and what the effects of G-force on a person could be. So now we're going to talk about the actual specific situations. So first off, in our car test, our dummy experiences about 17 G's over a tenth of a second. And this is in the pelvic area of the dummy. That's where I'm collecting my data from. As you can see on this graph, you can see how here, that's 17, that's 18. It's just south of 18, but it's around 17. And graph is in milliseconds, as you can see. So it's actually more closer to like a tenth of a second. And that's a lot of G's, because obviously that's like 170 meters per second force of acceleration. Now we're going to talk about other examples and how this compares to. So fighter pilots experience like a little bit more than half of that. They experience about 9 G's while they're going into vertical climbs. And what that really means is fighter pilots are experiencing a lesser amount of G's, but they're also still experiencing more than the amount needed to put someone into G-lock, which we're going to talk about in a second. And they're able to do this because of the special suits, equipment, and training they get. They get training to last through extensive periods of high G's, and they also have suits that are specifically designed to help regulate and prevent the acceleration from hurting them. Astronauts also have the same sort of training and equipment. And you can see during the space shuttle launch, they experience about 3 G's. And it's interesting to note that NASA specifically designed spaceships to go a certain speed and have a certain mass and all sorts of calculations to make sure that they stay around 3 G's, because the average person can withstand 3 G's. Some people that are very low on G resistance can go into G-lock because of this, but due to their training, most, if not all, astronauts are going to be unaffected by that amount of G's. Though you will notice like an increased amount of weight, as 3 G's, a person who weighs about like 100 pounds, say. Obviously, no astronauts can be weighing 100 pounds. You're not sending 100-pound people to Mars. But an 100-pound person at 3 G's is going to feel like they weigh 300 pounds. So obviously, it's a very large increase in the feeling of weight. Now, NASCAR drivers also experience that same amount at 3 G's, and they experience this during turns. which they experience an increased amount of acceleration. And obviously, this is much like the astronaut example, below the amount that an average person would go into G-lock. However, they also undergo special training because the training and the precautions prevent potentially dangerous catastrophes. Obviously, you've probably at some point in your life seen a impact or crash due to NASCAR, and those are usually not deadly, and usually they avoid serious injuries because of things like this that prevent not only those crashes from ever happening, but during those crashes, the drivers remain capable to react. Now, most people would experience G-lock with a loss of consciousness and vision, and this takes place between 3 to 6 Gs. Now, the average is about 5.4 Gs at 1 G per second, but obviously there's a greater range, and not everyone's the same. And what G-lock really is it messes up your blood flow. So instead of your blood correctly flowing due to your heart's pumping to your brain and your eyes, it doesn't, and it gets caught up in your lower extremities. So what this causes is you'll gray out or black out, and what this means is graying out is due to a loss of like a lower amount of blood, and your vision will become like dimmer. And blacking out is when your light receptors in your eyes don't receive any blood, so the ones outside will lose it first, so they'll go dark, and your vision will tunnel to the point that once the ones in the middle go out, you're completely blind. Now, there's usually a period of time between that and your complete loss of conscience in which you are still aware. So someone going through G-lock will first lose their vision. They'll notice their vision getting dim. They will then lose their vision, and then they will become unconscious. So now I'm going to talk about how this has to do with Newton's first and second law. So Newton's first law states that an object in motion will stay in motion, and an object at rest will stay at rest unless they're acted upon by an outside force. Now, that doesn't really mean much until I talk about the second law and how that interacts with the situation. So the second law says that the acceleration of an object is equal to the force of acting upon that object divided by the object's mass. So, for example, in this situation with the car, the mass of the person is dividing the force of the person. So it's the force acting upon the person divided by the person's mass, or in the more commonly used term, weight. Though those are different in this case, they act relatively the same because the weight is the mass. So your mass, which is calculated using Earth's gravity. So your mass, it's dependent on the mass. So the greater the mass of the person, the lower the force of acceleration will be. So as this person's weight would be to increase, the amount of acceleration acting upon them would be to decrease. So given like a standard 180-pound human, 17 Gs, which is about 170 meters per second squared, is acting upon them. And what this means is that a 180-pound human with 170 meters per second comes out to like about a 30,000 Newton force acting upon them in this car crash. So what this means is that as people are heavier or lighter, it changes the amount of acceleration, because the same force does not cause the same amount of acceleration. So there will be different amounts of G's due to different weights of people. So a driver who weighs 200 pounds would experience less G's than a driver that weighs 180 pounds. And a driver that only had 25,000 newtons of force acting upon them would have less acceleration than a driver of the same weight with, say, 40,000 newtons of force acting upon them. So, as the mass of the system, in this case the driver, increases, the acceleration actually diminishes, and the change in acceleration is less just drastic, and the health effects are lesser. But as the force increases, then the resulting health effects are greater due to the increased amount of acceleration acting upon the person. Alright, now I need to show my sources. And if you can barely see them right there, I'm going to change the color, and you will be able to see the big reaction. So there are my sources for this. That is it.